for help. He's around. So take advantage of his expertise and any thermodynamic, energy, cost calculations, things like that. I know some of you have already started this. So number two, if you build something, that would be fantastic. Show measurements, video, bring the demo. We can go outside if you have time and look at it, okay? If you build a prototype or even a mock-up, you know, you can just bring a mock-up if you want, or even detailed drawings and stuff. Number three, perform a simple cost-benefit analysis. And this can be very general. It really varies based on your topics as well. And you can ask me if you have questions. But I'm giving very general instructions here because you can interpret it the way you want. But definitely do the work. That's what I care about, okay? And of course, list your assumptions clearly. Okay. If you have questions after you think about this, email me, okay? Yeah, go ahead.
Still, 10 minutes.
Yes, everything is 10 minutes just because we don't have time. We have the teams, yeah. But of course, you can always give me extra material later, you know, by email if you want to back up your assumptions, whatever. It's perfectly fine. Or you can come talk to me. Huh? Yeah. Well, you should. Yeah, 10 minutes is a long time. Yeah, you should be able to show something, explain what it does. A practice. Yeah, oh, it's a skill you should develop, I think. Yeah. Of course, we go over a little bit. Okay, I'm not that strict, but you know, we want everybody to be able to present their case. Okay, so anything else? Oh yeah, a few other things. Then in November, we are going to start working on assignment 4, which is a commercialization part, and this will be very new to most of you, which is why I want you to start meeting with some mentors, starting the week before Thanksgiving. Okay. So I'm going to start assigning mentors, and I'll make an introduction. And they're typically, who are they? They are typically volunteers, local entrepreneurs who actually built companies and sold them, people from the technology venture commercialization office who have some experience with this. So take advantage of them. I'll tell you exactly what to do. But most importantly, you're going to show them your presentation and get feedback from them. And you're going to meet with them twice, once during this week at your convenience. You're going to email schedule based on your convenience and their convenience. You can meet remotely if you want. And then again, let's see. Wait. I thought there was one more. Maybe I messed up. I think it's the week after Thanksgiving, before your final assignment, but I will update that. Yeah. Think of them as mentors, where you're going to show them your presentation, your final presentation, and your canvas, which we'll talk about later on. Get feedback from them. That's it. Spend about an hour. Yeah. They have a lot of expertise, so try to take advantage of it, get advice and guidance and so on. Yeah. But I'll give you more instructions as we go along. But I just want you to kind of understand what we're going to do in November. Okay, the second half of the semester. Okay. So in the interest of time, let's jump in. Yeah, you can leave that. Yeah. Perfect. Yeah. So the first topic I want to talk about is something called optics for recycling. Now, this is a very interesting topic, kind of a little bit off topic from what we have talked about so far, but very, very important for resource management, as you will see, but also a huge industry, as you will see. Okay, and it's all based on this article here, which is already on the website. So for those of you who may not have read it, it's here. It's here. So click on that. Okay. Whoops, not there. A mistake here. So you will see the article, and I recommend you read it. Okay. So the idea is, when we have a recycling industry, how do we take advantage of exploit optics to separate the different materials that are being recycled? This is a big challenge, as you will see. Now, we'll start with something called reverse vending machines, which we have all seen in grocery stores and so on. And they're huge. It's a huge industry, by the way, which I didn't realize until I actually talked to some of these companies. The companies in the space are something you've never heard of typically. Envipco in the US, Tomra in Norway, which is they were the leaders, and they're the people who founded Tomra is the one who wrote the article. Of course, in the Scandinavian countries, they had big regulatory laws, basically, which forced them to actually have this in the supermarkets and so on. In any case, so we'll come to that also. So the engineering actually was driven by regulation, but also it also created some interesting business opportunities, which you will see. So the challenge here is the machine needs to identify and sort the waste. At high speeds in central facilities, as we will see. This doesn't have to be high speeds, and into multiple categories for recycling. This could be paper, glass, plastics, metals, any other stuff as well. Solution is optics. Now, the various optical solutions have been proposed. We'll talk about a few of them. Okay. First, of course, a shape measurement. This would be the simplest way to see it. Whether it's a can, whether it's a bottle, they're different shapes. So if you have some way to measure it, then you could actually identify them, right? High accuracy is needed because different cans can have different sizes. And one of the first solutions was simply a photocell on a conveyor belt. So the way it works is that you have a laser beam which passes from one side to the other side, and it's not shown here, and a detector on the other side. So as a bottle or can or whatever passes through, it is going to block the the signal, and by timing by knowing the speed of the conveyor belt and at what time the signal gets blocked, you can actually have algorithms which figure out, okay, what is the shape, what kind of material is, what kind of bottle it is. Okay, of course it cannot distinguish materials. That's a big limitation, and it's a pretty expensive technology. Another advancement that happened is something called laser range finding, which is actually an interesting technology in itself. And I won't go into much detail because this requires a little bit of understanding of something called physical optics, which we haven't learned in this class. But the idea is quite straightforward. You take a laser beam and you modulate its intensity. In other words, you turn it on and off, like a sinusoid, okay? And then the light hits, the laser hits some material and it comes back. Okay, it reflects back. Now the detector sees the reflected light. The reflected light also has this modulation. Now, based on how far the light traveled, this phase of this modulation changes. So if the light traveled a farther distance, okay, so let's say, imagine you have a bottle which looks like that. If the light reflected off from here versus here, this difference in distance will show up as a difference in the phase of the reflected wave. And by knowing this difference and some calibration, you can figure out what this distance is. Okay, that's the basic principle. But of course, generally speaking, it's a bit more complicated. Now, you can see an example of the system here where there is it's a crate. So you load the entire crate in, and then there is a laser beam that scans in an arc, okay, which is pretty big. It's a 50-centimeter radius. And then it measures the reflected light at every location and builds up a 3D shape. Okay, that's a simple example. Yeah, I'll skip that. It's not so important. A more advanced approach and a cheaper approach is to use stereo systems, vision systems. So the idea is simple, just like our eyes. You can combine two cameras and image processing for fast, accurate shape recognition, because our eyes, our brain can distinguish 3D in exactly the same way. Yeah, you can build 3D as well. Nowadays, this is of course very common in video games and so on, right? So for those few might have played the Microsoft Connect, I think, or maybe it's the Sony. Can't remember, but they do have two cameras, infrared cameras, which just allow you to recognize your hand gestures and things like that. So you don't need a controller, right? You can control if you're playing tennis, for instance, you can control with your hands. it works the same way. And the principle is simple, just like, you know, because if you only have one eye, your perception will be the same independent of depth. But because you have two eyes and your brain actually superimposes the projected images from the two eyes, you actually have a perception of depth. And this is, by the way, you know, what people utilize for augmented reality and virtual reality systems as well, kind of, for instance, in these examples. So very interesting optical systems as well, obviously. Okay, coming back to the point about markets that I mentioned before, there are some very interesting things about the recycling market that we should be aware of when one thinks about the technology. One is this is something called single use versus multi-use. Single use, of course, means that you don't need to be careful about the material that's collected. You can crush it, right? Aluminum cans, for instance, and make it easier to transport. But if it's multi-use, like beer bottles, for instance, they have to be transported carefully because you have to wash them and reuse them, ideally. Right? The second thing is that lots of states, of course, have container deposits, right? I forget, in Utah, do we have it? Don't remember. Probably not. Maybe not. Okay. So in many states, there's a container deposit. What that means is that when you buy a bottle of beer or a can of Coke or something like that, you pay an additional few cents to buy it. Those few cents go to the government, but you can get those few cents back if you return the can or a bottle or something. Okay, this is what's called a deposit, because so you don't lose the money. But what happens typically is that roughly 90% of the people return the bottle, all the bottles get returned. Roughly 10% of these, on an average, don't get returned. What does that mean? That means 10% of those sales, that money, a few cents, remains with the government for free, right? No one comes to claim it. And that money is actually utilized to actually support all this recycling infrastructure. So there's a very interesting logic to this as well, because it's the non-participants who actually finance the whole infrastructure. The infrastructure is expensive. It's a multi-billion-dollar industry, actually, around the world. Okay. Of course, in non-deposit markets like ours, in Utah, for instance, the commodity prices drive this industry. So, you know, whatever the recycling companies can get very, very pure aluminum, for instance, they can sell it for whatever the commodity prices will bear. Right? So that drives the economics as well. So in that situation, the purity of the return materials is very important, and you can charge higher prices based on the purity. Very important, of course, for metals and things like that. So in all cases, the accurate sorting and efficient transportation are the key driving factors. So those are the two most important cost drivers. Of course, we are not talking much about transportation, but we want to talk about sorting. Yeah.
A question on return deposit on the bottles. So who's controlling that? Who's saying you have to do this thing? Because this is nothing new. This is invented.
Yeah, 50 years ago. Yeah.
Still active in Europe right now.
Yeah. No, in most of the U.S. also. Just yeah, but it's a state law. So if you're in, for example, I was in Massachusetts last week. I think the bottle deposit is 5 cents. I think they're different, but so yeah, so Utah has this too. Yeah. So, but it's a state law. It changes. Yeah. And the money goes, because the retailer is supposed to collect it, but the money goes to the government. It's not like the retailer gets to keep it. Political reasons, but generally speaking, because the argument would be it's an additional tax on the consumer. Right? But yeah, I mean, there are different reasons, but that's generally the point. So the sorting of materials like metals or paper is not too difficult, because things are very different, right? You have transparent, or it's highly reflective and so on. But sorting of plastics is very complicated because they all look the same, and different plastics have very different price points in the commodity markets. So you can get a much higher price for PET versus, polycarbonate versus PET. Right? Just because the quality, the life cycle of the certain polymers are longer than others. So they have and this is why you see, if you look at the bottles, they have different numbers, right? 1 to 6 and so on. So the question becomes, how do you distinguish them? Because they all look the same, right? So you distinguish them with something called near-infrared spectroscopy. So obviously an optical solution. And the idea is quite straightforward. If you shine a laser beam through the plastic, you're transmitting the light through the plastic, okay, it's transparent. And if you measure how much light is transmitted, it changes with wavelength. So this is changing wavelength from 1.5 microns all the way to 2 microns, okay? And if you measure the transmittance, it has some signature here. It's hard to see, but the different plastics have a very different signature. So by looking at these signatures, you can actually tell them apart. And this is an important concept. This is a very important idea. Of course, this idea is very widely applicable, not just for recycling, because people use it for everything as different as cancer detection to air quality monitoring. All of this utilizes spectroscopy. But in recycling, it's a very unique problem. So these are all different kinds of plastics. They all look transparent: polycarbonate, PET, polyethylene, PVC is of course common. All those kinds of PS, polystyrene. How does this work? There are different ways of incorporating it. So these are good examples of optical systems as you start thinking about implementation in your own projects. One is something called correlation spectroscopy. It's relatively inexpensive and simple. It basically uses a filter wheel. So essentially what happens is you have a laser beam which goes through the plastic bottle, let's say. And then you have a reference beam which goes through this filter wheel. And then there's a detector, 2 detectors, which basically measure them both. But sometimes it's one which is measuring both with the beam combiner or whatever. Now, if it's calibrated properly, this filter wheel, you can see, has multiple windows in it, right? And this filter rotates. When and of course, that means when it rotates, the signal in this detector changes, right? You get different signals. When one of these signals matches the signal going through the bottle, then you know it's the same material. Of course, it's a difficult problem because you have to calibrate it carefully and so on. It can be done. It's a bit more complicated system than this, but that's a simple idea. So you simply spin it. Of course, it can be very fast, right? So this bottle simply goes through like a conveyor belt, some kind of machine. Obviously, this is from the Norwegian company, passes through. It matches the plastic, and then it goes into the correct container behind. Yeah.
How efficient is the system? I mean, I imagine it depends on the thickness of the material as well, right?
That is a very good point, which is why I was saying the calibration is very critical. So you can see, that's a very good point, actually. You can see when you put it into the machine actually controls exactly how it passes through the laser. So it doesn't go through at an angle or some weird way like that, because that'll affect the transmittance. So it's very highly controlled how it goes through, and so you can actually compare it very carefully. And that geometry is fairly carefully calibrated. That's a problem, and not always reliable. And this is generally turns out to be a fairly big machine, somewhat inexpensive, but this is a very novel solution that, again, a Scandinavian group came up with. I think it was a company out of Sweden, if I remember right. They used something called a diffractive optical element. Now, this is like a prism or a grating. It takes the light, okay? DOE is a diffractive optical element. It reflects it, so it's coated with some metal, so it reflects the light, but it also disperses the light. So different colors or different wavelengths get dispersed in the vertical direction. Now, in addition to that, as the bottle moves through in that direction, this thing is rotating. This is kind of vibrating. And when it vibrates, different wavelengths pass over the bottle, or at least one point of the bottle where it's measured. So you get the spectral information very fast. This can vibrate really fast at megahertz rate. Okay, so it's a very clever, compact, and this can be quite cheap. The idea is that you can stamp them out like CDs or something. It's a very simple system, but very clever innovation. So in this case, the single DOE can be used for beam splitting, which means that the different wavelengths are split up. The spectrum separation, which are the wavelengths, sorry, and also focusing. So it's taking the source and focusing it here. We'll see this type of an idea again next week when we talk about spectrum splitting for solar concentrators. It's a very similar sort of idea we're going to apply to solar cells. Of course, in most situations, this happens at the very large scale. So Salt Lake City has a municipal waste, I think it's called a recycling center, which are huge facilities, multi-billion-dollar facilities. These large-scale facilities contains lots of resources, valuable metals and so on, but they're mixed with other stuff. So you need to be able to separate these out very, very fast. These have to be very fast, right? So you're talking about 30 tons of waste per hour. You have to get near IR and visible spectra really fast, because near IR to separate the plastics, visible to separate colors. So you might have green bottle versus brown bottle versus transparent bottle and so on, right? So you might want to separate those things down. And you want these to be captured with high spatial resolution, because you also need to get the shape, right? And it has to be very, very fast. Meters per second, typically, it's, kind of fast. The reason, of course, is that you have commodity prices. These are old prices, but aluminum and PET plastics can also be higher. They're recycled typically, right? And this is what one of those systems looks like. It's a huge facility. Here you can see an example of some waste coming in, going through a big conveyor belt. There's the scanner, similar to what we saw in the last two slides, which does the spectroscopy. Okay, and then based on the detection, whatever the decision is made. So typically nowadays there's machine learning to make this decision, right? There's neural networks, which will decide, oh, okay, this is at this instant of time, I have a plastic, at this instant of time, I have a bottle. So a pneumatic jet will simply push it into the right container. So very complicated system, very, very expensive, huge industry. None of it, we don't really think about it, but it's a lot of optics and of course controls here. Okay, the last thing I want to show you is this video, which was prepared by a team like you about 3 or 4 years ago, who took on this as their project topic. And I just want to show this video. It's about 5 minutes, but it'll give you an idea what I expect for the final video. This is a little long for my taste. It'll give you an idea. So treat this as just an example, but also deals with this topic we're talking about. So hopefully, two birds in one stone. So I'm gonna first disconnect that. Oops. And let's play this.
Introduce you to a distributed optical plastic sorting method by simply reading the SPI resin code on consumer plastic waste. Distributed Plastics LLC is backed by Bing Shen, a PhD candidate, and Joseph Bogue, a master's degree student, both at the University of Utah's Electrical and Computer Engineering departments. Currently, consumer recycling is done in a big box manner, whereby large trucks go from house to house picking up recyclables. They then take these recyclables back to the plant where they have to sort them, compact them, and bale them for sale. Although this big box sorting method is proven day after day, these sorters are expensive because of advanced methods of discrimination. These sorters use visual and infrared wavelengths, spectroscopy methods where actual elemental makeup is determined, X-ray imaging for difficult materials, and lastly, the human element for anything that might have been missed. Although these big box sorters are marvelous feats of engineering, they come at a large monetary cost, both initially and through time. Now, in a recent case study done at Salt Lake Municipal's Recycling Center, they recently made a $7 million sorting capability upgrade. This upgrade is a great improvement for them. However, if recycling in general is done in a distributed manner instead, these types of costs can be greatly reduced. Now, before we get into the innovative technology, we need to review plastic resin. Remember that plastic is a synthetic material made from a wide range of organic polymers like polyethylene, PVC, and nylon. These polymers can be molded into virtually any shape and are easy to recycle if kept in the same resin family. This is why it is important. Keeping these polymers together allows for efficient recycling and more dollar per bale. Notice the code, the SPI resin code on this plastic bottle. Now, simply put, our innovative idea is a smart garbage can. This smart garbage can will take your plastic bottle, find and read the SPI code, and drop it into the appropriate internal compartment. It is centered around consumer plastic bottle waste and will automatically sort it as you walk away. It has 8 columnar sections, 1 for each SPI code and 1 as overflow, with a center hollow section that will contain smart electronics. Above this center columnar section is a domed top with an enclosure that holds the plastic bottle on an incline. When the bottle is dropped in, the algorithm reads the SPI code from the image, determines which bin to rotate towards, and opens a door and lets gravity take over to do the sorting. Notice here in the prototype overview, a high-resolution camera sends an image to MATLAB. The patentable detection algorithm then decodes the SPI code and sends that value out via serial data to a microcontroller. The microcontroller then drives a stepper motor and actuates a door to open, dropping the bottle and sorting. Actual prototype results show a noise-induced hand-drawn images sent to MATLAB. MATLAB detection algorithm successfully detecting the SPI code and sending that data via serial to a microcontroller. The microcontroller then correctly drives a stepper motor to the correct SPI code location, and a LED will blink showing or simulating that a door has opened. Now, our claim with this market potential is that Salt Lake County conservatively has a potential for a 30% increase in volume and a 3x decrease in cost if using a distributed plastic sorting method. The nitty-gritty of this claim follows. Salt Lake Municipal per week has a conservative capacity of 336,000 kilograms per week. Another conservative estimate of our distributed methods shows 431,000 kilograms per week, depending on the volume. Another conservative estimate over 30 years shows our distributed method costing $22 million, whereby the large big box sorters.
Yeah, I'm gonna skip that, but you get an idea. Yeah.
That video is
That's the very last one. Good. Actually, 4 is actually bad, but I expected to submit a video as part of the final assignment. It's actually do the next step. This was part of that. This is a little long for my taste. I would prefer shorter, but if you get an idea, right? I'll give you more instructions as we go along. Any other questions? Okay. The last thing I want to show you is an actual large area optical sorting system, not just for the recycling, something completely different, but also a giant industry. I just want you to be exactly aware of all these different things. Let me just pause this too loud. Sorry. Yeah, go ahead.
So they have a device that can sense where the bad grapes are and then force
It's nothing, it's not magic, right? The camera. It's there, it's visible and infrared camera. So there are multiple cameras, very, very fast cameras. That's all right. And they have algorithms which work in the background. So really, really fast. Mostly, I don't know exactly, it really depends. But most of the time it's spectrum, like I said, the spectral signature, plus the color images. So some combination of them. And then, of course, then the jet has to come in and this whole feedback control loop has to be so fast. So this is what I'm saying, it's a very complicated engineering system where optics, of course, plays a very important role. Obviously, a very big industry as well. Oops, let me see what happened there. And that, I think, was the last slide. Okay, great. Now, so that was, let me hide this. That was all that we had for the recycling. Okay, so you get a picture. I want you to get a flavor for different things which you might not have thought about. The second topic I want to talk about, which will be the rest of the lecture, is on anti-reflection coatings. Now, this is more related to what we have done in the class, not as applied, but obviously also quite important, as we'll see. Any questions before I move? Okay, guess not. So, what is anti-reflection? Of course, anti-reflection, as the name sounds, it's prevent reflection from surfaces. So here you can see this glass has reflection. You can see something reflected off the glass. This glass does not. And that's a big problem. So for people like me who wear glasses, I have to pay extra to get this anti-reflection coating on the glass to make sure I can get as much light as possible into my eye. Okay, otherwise light will reflect off and I will not see properly, especially at night or low light conditions. That's the idea. So here there's more examples of what it would look like. You know, you have glasses with anti-reflection coating, AR, without. You can see the differences. Sometimes they also have the anti-fogging, as you know, from skiing, ski helmets and so on. You can also have the AR, which will reduce glare. And same thing you can see in the eyes as well. How does it work? Whoops. So the way it works is roughly shown here. We'll go into some more detail. Whoops, why is this? Some reason. Zoom out a little bit. So here, light comes in. So that's some sort of cover on top of, let's say, your eyes, a sensor, or the solar cell. Of course, also important. If you don't have any coating, 4% of the light's gone, and 4% comes from the refractive index of glass. And it's approximately, the reflection loss is n-1 by n+1 squared. We saw this before. If you put n equals 1.5, you'll end up with something like 96% transmitted. Okay? But if you put an AR coating, you can reduce that to almost 0. so everything goes through. It's very important, of course, if you have a solar cell, right? You want to get everything through. You don't want to lose light on the top. And that's why we're talking about it. There are various technologies used for anti-reflection coatings. We'll talk about 2 or 3 of them. First is what's called quarter wave coating. To understand this, first we need to understand the phenomena of interference, which we haven't talked about because comes from physical optics, not geometrical optics. Now, physical optics is the science where we take the wavelength of light into account. Whereas in geometrical optics, we ignored the wavelength of light, the extent of the wavelength of light. We assumed that the wavelength was too small to be of importance. So we're gonna play a little video here to explain interference. Okay.
In this video animation, we will be able to see constructive and destructive interference. You'll notice at the bottom of the screen that we have 2 waves, wave 1 and wave 2. Each of these waves has the same amplitude of 50 units here are irrelevant. And the picture above here shows us what the 2 waves look like when they're added together. And so let's see what happens when we change the relationship between these waves. If I move the waves so that they are in phase, the amplitude of the wave, the resultant wave, increases. So now the amplitude is very large. If I come down and I start to move them so that they are out of phase, we can watch the top of the graph, and we can see that the resultant of these 2 waves, when they're added together, starts to change. And so it gets smaller and smaller and smaller. Eventually, when they are exactly out of phase with one another, the resultant is that we get destructive interference, and we have a resultant wave of 0. So when they are out of phase by 180 degrees, you get a resultant of destructive interference with 0 amplitude. And if we move it back up to where they're in phase, the resultant is that we get constructive interference and we get the maximum amplitude.
Okay, so that's the idea. So an anti-reflection coating would be where you want the 2 waves to destructively interfere, right? So what we're trying to do is, if I have a surface, let's say that's my solar cell. What I want to do is I want to make sure the light that reflects off from here, and let's say I have a cover on the solar cell, and the light that reflects off from the bottom here will destructively interfere with each other. If I'm able to interfere this light with this light destructively, then I will get 0 coming back. I get 100% gain. This is the idea. Okay. So then the goal is how do you do that? So the pictures here. So I have 2 interfaces. I have air on the top, refractive index of n prime, which is my glass, and refractive index n, which is my silicon solar cell. So the question is, how thick should I make this glass to ensure that light isn't destructively interfered? So let's see if we can first think about it. What does destructive interference mean? Right. They should be phase shifted by 180 degrees. Right, which is what? So, but what does that mean in this case? Someone said that. Lambda. Yes. So you know the wave has a wavelength, lambda, and this is in phase with this. That's when the phase matches, and this will be out of phase by pi. Not so clear. It's lambda over 2. You want this ray B to be out of phase from ray A for half the wavelength. So this distance should be what? How many times is ray B going through that distance? 2 times. certainly you need to have 2 times somewhere there, right? 2 times d should be half lambda. However, you also need to take into account that the refractive index is a prime, it's not 1. Right? The refractive index will shorten the wavelength, or it will go up here, because you can think about that as the optical path length. Right? Remember we talked about distance times the refractive index being the optical path length. So then d becomes lambda over 4 n prime. Okay. So the idea again is that the rays A and B are out of phase by pi or lambda 2 and the structural unit. Okay, so there are 2 important concepts here. One is the path length difference has to be half lambda. Second, how do you compute the path length difference? Light shall come through twice through the material whose refractive index is impact. Okay. However, this is not a perfect solution. It only works for one angle and one wavelength. If I change my wavelength, if I come in at a slightly different angle, this is no longer true. Right? You can see this. If I draw, so I'm going to draw the exact same thing we have there. So refractive index is 1 and prime. And if I come in like this, everything is good. Right? This interfere and cancel out. What if I come in like that? I will refract in, reflect out, and refract out. My path lengths are no longer matching, right? Something is different. How do I compute my path length now? You should be able to do it. I should do this to good practice. Can you guys try? I'll try to write it down. Take 30 seconds. In fact, that's my next question for you. Actually, I'm going to. I should go back and have you let me draw it. So it's, how do you compute the optical path length here? My angle here is theta. This angle is called theta prime. First of all, find theta n prime times sine theta prime is sine theta, right? From Snell's law. And my path length, so this distance is d. My path length is this. I'm going to call this A, B, C. A, B, this is 90 degrees, this triangle. AB plus BC times n prime. This is my path length, right? Path length. So that's n prime times AB is what is this? 10 theta prime. Is it tangent? Cosine. Right? Cosine is d over this. So this is d divided by cosine of theta prime. And this is also the same. It's symmetric. C n prime d over cosine theta prime. Is that okay? I want this now to be equal to lambda over 2. Because I'm trying to make sure these interfere constructively. So the consequence of this is the fact that the thickness is not general. It only works for one wavelength, one angle. If I change the wavelength, okay, I designed my coating to be perfect here at 0.6 microns. If I change my color a little bit, no longer do. Okay, that's silicon in the glass with optimal anti-reflection. And it's also depending on angle.
By the way, if you don't use any anti-reflection coating, the reflection is huge. This is for silicon. As we know, the silicon looks like a mirror. Most of the light's reflected is because of the high refractive index. It's also dependent on angle, as we know. You have a small angle, there's a small amount of reflected light. A large angle, more light's reflected. By the way, this is very easy to see. If you look at that piece of glass, the window and the door, if I stand right against it, I don't see much reflection. But if I go way over here, and in fact some of you can look, and see reflected light on inside there. This is a consequence of something called the Fresnel reflection. Light, the amount of light that's reflected changes with the incident. If I plot reflected versus standard emission, it goes up. So I need to somehow solve this problem. I have to solve, because in a solar cell, you're not a choice. The sun's moving. You come at any angle. It's very broad. It's not just one color. You have to somehow put a xenon anti-reflection coating that will work for all the colors, as many angles as possible. That such a solution does not exist, by the way, theoretically. But you can get some good solution, good enough solution, which is used in all solar cells today. Okay, one idea is to put what's called silicon nitride on top of the silicon cell. Now, silicon nitride has very good properties. It actually acts like something called a passivation layer. It reduces the defects on the silicon crystal here. Okay? And those effects in silicon crystal are very bad for a solar cell. We learned this in a lecture in about 3 weeks. But the silicon nitride can be used to minimize those effects. But we can also use this to act as an anti-reflection coating. So this example, what is the thickness of an anti-reflection coating? For silicon nitride, reduce reflections on the silicon surface at normal incidence, not 45 degrees. Let's try to do this. At normal instance, we already know how to do it. 2D tangent prime is lambda over 2. Okay, and we solve that. We already did that. At oblique incidence, we also did that. Exactly the same. 2D tangent prime divided by cos cube is lambda over 2. This is just to illustrate the same point. That is, D is dependent on lambda cube. So not that useful. So how do you solve this? Well, all the notes are already posted online, so you can get them. You can solve this problem somewhat by an idea called index matching. The idea is based upon this. The first try to understand why is the reflection happening. The reflection happens because you have a change in index. Right? Let's say you have a silicon solar cell whose index is, let's say, 3.1 or some pretty high number. If I'm out here, this is air, my index is 1. Or a huge change in index. So instead of having this huge change in index, if I could incorporate some material here, whose index is between 1 and 3.1, I can minimize or slow down that change. That reduces, you can show theoretically that will reduce the amount of reflection. And this idea is called index matching. We're trying to match the index of the air. It's kind of like impedance matching for those of you electrical engineers who know it in antenna. And they're all connected, by the way. Because, of course, antennas deal with electromagnetic waves, which is the same as light. They're all the same. So that's the idea. So of course you can do this in many ways. One is to use multiple layers such that the index varies smoothly from one to n. So let's say this is silicon, and then you slightly higher index, slightly lower index, slightly high, slightly even lower until you get to 1. Multiple layers, you have this beautiful adiabatic smooth layer. And if you do this properly, you get 0 reflection for all angles and all radius. And that's the ideal solution. You cannot make it continuously there. That's very difficult to do. And no material other than vacuum has an index of 1. Right? Doesn't exist. Vacuum or air. So it's actually very, very hard. Now, this idea works for all the wavelengths as long as the index is not changed. This is referred to as incoherent compared to the quarter wave interference that we talked about before, which is referred to as coherent. Just terminology, not so important for us. So there's no interference effects in this case. So there are other ways to achieve the same effect. As you can imagine, this can be a very expensive proposition for deposit hundreds of layers or something. That would be very expensive. We can't afford to do that in a physics service. There are other solutions, and I'll just point them out. One option is to grow some grass at the nanoscale. Very rarely grass at the nanoscale. What does that do? Simply speaking, it takes, let's say, silicon, and you etch the silicon to form. It's almost random, but let's imagine it's a cone. If I take a cross section up here, most of it's air, right? The little dots of silicon, right? Just at the tip. And then if I start going down, I see more and more of silicon, right? Look like that. If I go even more, I see more of silicon, right? Until I come down here, everything is silicon. You see, as I go down here, I'm going from an index of 1, all air, a little bit of silicon, more silicon, until everything is silicon. That's gradually varying index. Now, if you do it at small enough scale, it will behave like a smooth variation of index, which is exactly what they do. Of course, they do it randomly. Doesn't need to be this nice pyramid from the random. And this creates what's called black silicon. It's a very important advancement. It was accidentally discovered, by the way, by a group at Harvard. They formed a company called Psionics to commercialize black silicon. And they claim to have the blackest material on the planet, which is a very difficult thing to do. So you're trying to absorb as much light as possible. This is some work from, I think, from the National Renewable Energy Labs, which is of course based in Colorado. So you can see the difference between black silicon, which looks like that at the nanoscale, and regular silicon, which is flat. That looks like a beautiful flat mirror. You can see his face. The mirror reflects huge amounts of light. This is black. It's a black hole. It absorbs everything. Yeah.
So you use a material that's not anyways. Better.
But you want it to be a good semiconductor too. Right? You want it to be a good solar cell. So not everything is a good solar cell. Silicon is probably the best solar cell.
Carbon nanotubes.
Carbon nanotubes are good candidates. People are looking at it. Unfortunately, they are really hard to manufacture at large scale. And they have other problems in terms of the current and so on. But yeah, definitely. Lots of people are looking at it. You need a good semiconductor because remember a solar cell. We will see this in about 3 weeks. Solar cell needs to form a good PN junction. For those of you who are electrical engineers, appreciate this. You've taken 3200. Has anyone taken 3200 or not? Yeah, there's some of you have. So you know what I'm talking about. There's a, well, if you haven't taken it, it's fine. Basically, it's just the fact that you need to create a PN junction. You need to have highly doped with electrons on one side, highly doped with holes of vacant electrons on the other side. You need to have this junction. This is what creates a solar cell. And we'll have a lecture on this. So that requires some specific material properties, and silicon happens to be the best one.
They can dope these black silicon.
Yes, I mean there are problems, of course, but imagine the way, of course, in this case they are They care only about the top surface. So the junction can be down here in the bulb, right? Maybe like this. But that's a good question. There's lots of architectures. It's not a simple solution. And black silicon made by psionics is, I believe, today not used for solar cell, but for very, very sensitive camera sensors. For most of the military applications and so on. The idea is that even under moonless nights, we can still grab sound light enough to form some images. That kind of application. It's similar, right? It's the same idea. You're absorbing light. You can also do this in other ways as well. You can imagine structuring, choosing the geometries of the nanoscale in order to incorporate this idea of anti-reflection. So, for instance, here they have a hexagonal lattice of pillars of silicon, which forms a surface which looks like that. But simply changing the lattice structure at the nanoscale, you can make it darker. You can also control this at the nanoscale as well. But this is, of course, area of research that people are still working on. I would say the vast majority of commercial solar materials simply use some sort of random effect. Because it acts both as an anti-reflection coating, but also useful for light trap in the previous lectures. Now, the last part of this class, I want to do some simple quantitative analysis, which is taken from the paper from the Ivlanovich, the same paper that we did for light trap, so the section from that paper. So we know some of the terminology is exactly the same. So the system we're going to look at is shown on the top. We have air that comes in. There's PMMA, which remember is polymetal methacrylate, which is plexiglass. So it's the same material as plexiglass. And it is texture at the bottom, and then there's silicon. That's our cell. We're trying to maximize by going into it. That's the goal. The factor index is 1 of air, 1.5 for PMMA, 3.5 for silicon. Now let's define some variables. P incident is transmission from air to PMMA, the top surface, top interface. Air is the absorption factor of the rear surface of the PMMA, which includes transmission into silicon. And the reflected light is simply 1 minus air, right, reflected in the surface. Air is going down, 1 minus air is going up, times P. So, using this idea, we can follow the ray. So light comes in, okay. Some of it goes into silicon, which is P incident times theta. P incident times 1 minus theta goes up. And then it reflects off that interface with an efficiency as 1 minus theta times T incident times 1 minus T escape rate squared, which comes from the escape point, the critical angle, right? And then it happens again. Same thing happens again. You multiply theta T incident times that's the second observation. And so on and so forth. It goes forever. Right? So you can write a geometric series here. If you do this P times, the Pth absorption looks like that on the top. Okay? And I can write out an expression for the total absorption, which is simply theta times T incident times 1 plus 1 minus theta times this stuff plus 1 minus x squared times this stuff squared and so on. Infinite series, infinite geometric series, which we all know we learned in high school how to solve. Take this. This is the rate. Because 1 minus r. So that is the 1 minus the rate. Okay. That's really simple. So that now gives us how much light is absorbed within silicon in the presence of an anti-reflection curve. Okay. Now we can throw in some rough numbers. For PMMA, eta is 1 minus that difference, and the difference of factoring is someone factoring is squared. We end up with something like 84%. And T incident is 96% because it's going from air into the plastic. Okay, you can plug in those numbers. So eta is 84%. T incident is what's coming into the plastic. That's 96%. Remember, 4% is lost. And T bar escape and T incident, they're going to say approximately the same. You plug in the numbers. So you plug in all this stuff. This will cancel out. You will end up with something like 92. Now this is very nice because if you do nothing, this number will look like 70%. That means 30% of the light on a bare silicon will simply get lost. Won't even enter the cells. That's completely. Here you reduce that base to about 80%. This is quite nice. Very important. So just put this into words. But 90% of the light gets absorbed in silicon and the PMMA silicon interface, which is what you want. About 10% of the light is reflected back. So PMMA on the top of randomly textured silicon acts as a decent IRC. IRC stands for reflection. Note that if no PMMA or texturing was present, the reflectivity of a polished silicon wafer, which would look like a mirror, would be just that. Silicon minus air by silicon plus air squared plus 31%. That's a huge list, obviously. So the take-home message is that you want to make sure you have an anti-reflection coating in addition to the texturing which is used for the anti-reflection coating is to ensure that as much as possible enters the system. Now we can also put try to do a calculation and optimization to understand what kind of anti-reflection coating would be best. Okay, so that's this example here. Simple index matching. Design an ARC for polished surfaces. So we're going to ignore the texture in this example. So one, some refractive index n, which we don't know, that's a question mark, unknown, and some refractive index is 2.5. What is the total loss by reflection of the ARC? What is the total loss? First of all, what kind of ARC should we put there? What is the total loss? Okay. I'm going to show you how to do it, but since we already had the exam, you can ask this, but you should know how to do this. Obviously, before we do anything else, we know intuitively that this index has to lie in between these, right? We know that. So because we want something in between. If it's less or more, it's not going to help. In between, you can choose in many different ways. You can choose the arithmetic mean or the geometric. Typically, for most of these applications, which I'm not going to go into why, a geometric mean is used. What that means is that n is typically chosen as square root of 1 times 3.5. That's a geometric mean. It can also be, of course, the arithmetic mean, which is 1 plus 3.5 over 2. The average.
No, we're not having those two.
You can. But I think, I don't recall exactly, but mathematically you can show this is reality. I think, I don't remember exactly. So, the example we use arithmetic mean. So, not the best, that's it. So, arithmetic mean given 2.25, so you can now calculate the loss. Reflection from the top surface will be, so let's first draw what does this mean. We all understand what is it that we calculate. So we have two interfaces. We have one which is air, and I have a refractive index of 0.25, and I have silicon 2.5. Question is, how much is lost here? How much is lost here? This is the question. This is simply 2.25 minus 1 by 2.25 plus 1 squared. Okay, so that's what's calculated here. The reflection 1, 15%. Reflection 2, 15, 2.5 and 65, 7.4%. Total loss, we're going to add them up. It's approximate, not exactly true. If you add this, what's that? Approximately, and exactly true. You get something like 22%. Okay. So you see what happened without using the text, with using the texturing, this number was Remember the answer previously when we had texture in here, and I was using here, A was 92.3, right? And so 100 minus 92.3 is what? 7.7. So this was the loss. Now my loss is 22%. So texturing is important. That's what it shows. So texturing helps that additional amount. And that's what this statement is saying. So let's read it, make sure we understand. That's the last slide.